Hello and welcome to the Change in Elastic Energy video tutorial. Here we have a spring that is displaced 40 centimeters, and we have that same spring displaced 10 more centimeters, and we're going to find out how much elastic energy was required to stretch the spring that additional 10 centimeters. So we're going to start with our elastic energy formula. So elastic energy is equal to 1/2 kx squared, and so elastic energy is equal to 0.5. And now we need K. K is the spring constant. So that's how much force is required to stretch the spring a certain amount of meters. And we don't really have K, but we can get it from the data provided. So if we can find the amount of change in newtons for every meter, then we're going to get the spring constant. So that's basically the slope of the line that compares the displacement and the force. So let's find the slope of the line. So let's see here. 0.1, 0.2, and so on, because we're doing meters and not centimeters. So 0.5, 0.7. And now let's enter how much force. So at 10 centimeters, there was 300 newtons, and then it went up by 305, and so on and so on. 1230, 1487, and 2079. All right, so I don't need that anymore. All right, let's make it visible, and there is our best fit line. So it looks like our slope is 2976. So 2976, and we are going to put in 0.5 for our displacement, because that's how much the spring is displaced, up to 0.5. So we're going to find out how much elastic energy is in the spring at this marker right here. So let's see, 0.5 squared is 0.25 times 0.5 again for the half, and times 2976. It gives me 372 joules. So that's the elastic energy in the spring here. Now let's find out what the elastic energy was in the spring before we even started to pull more on it. So elastic energy, 1/2 kx squared. So it's doing the same thing we did before. So it's 1/2, and the spring constant is still 2976. I mean, that's going to be the spring constant at all times for that spring. But this time we want to know, what about when it was at 40 centimeters? So 0.4 squared should be 0.16, and it does, divided by 2. 0.08 times 2976 gives me 238.08 joules. So this is the elastic energy at this point. This is the elastic energy at this point. We want to know what was the change in elastic energy from here to here. So that sounds like subtraction. So the change in elastic energy is equal to 372 minus 238.08. So just really quick. Alright, I get 133.92 joules, that seems about right, for the change in elastic energy. So that's how much elastic energy from here to here was put into the spring. We're going to check this answer graphically. So remember that answer, 133.92. So here on our graph, we can find the elastic energy by taking the area under the curve. So here's our curve, and we're going to take find the area underneath. The name for area is integral. So we're going to take, see how it shades in the area, so it's calculating that area. So the area is 720, which is not 133, but that's because it's taking the area from 0.1 all the way to 0.7. So that's how much elastic energy is in that region. So let's see here. Let's change our range from 0.4, and this here should go to 0.5. So it's a bit of an estimate, but we get 134.1. Calculated out, we got 133.92, and those are extremely close. So that has to do with estimation. If you actually look carefully, you'll see that it's taking the connect the dots line to calculate the area, and it's not actually taking the best fit line. And I'm pretty sure that's where you're going to get the error in your results, aside from the fact that I'm pretty sure I'm not at exactly 0.4 and exactly 0.5 doing it this way. If you don't have a program to get it, we could have just taken the, let's see, it's on a scale, this 0, get 0, 0 in here. You could have just calculated the area of this triangle here. So 1/2 0.5, that's the base, times whatever this value is here, 1487, will give you the area of our big triangle, all this, and then you can subtract off this little triangle here. So why don't we do that really quick just to see that works. So we're going to do 1/2. The base was 0.5. Whoops. 0.5. And the height was, let's see, at 0.5, we're at 1487. 1487. So that gives you 1487 times 0.5 times 0.5 gives you 371.75. And for our little triangle, that would be this triangle here. That's 0.4 times 1230 times 1/2. So 1/2 times 0.4 times 1230. So 0.4 times 0.5 times 1230 gives me 246. So the change in elastic energy should be the big triangle, so 371.75, minus the little triangle, 246. So 371.75 minus 246 gives me 125.75, which is close. It's a little off. So probably should have not used the data table to get these numbers. I think that's where my error is coming from. I probably should have used f equals kx to get my numbers using the k value, 2976, and probably would have gotten there, but still it's in the ballpark here. So that is the that's doing it graphically, taking the area of this triangle here and subtracting off the area of this triangle here. So there you go. Thank you for watching the Change in Elastic Energy video tutorial.